Okay, so let's start. So the last class, right, we did what is called the canny, right, edge finder, and you saw, right, I mean, how you can flag edge pixels both weak and strong using what is called, a linking this one mechanism. Now, the next obvious thing to ask is, can I get a solve a similar problem using what? A deep network, right? I mean, since you've done deep networks, right, already. So let me so right, so we want to see, right, how would one employ a deep network in order to solve this problem, right? So suppose I asked you, how would you do it? Suppose you wanted to solve the same problem using a deep network, right? I mean, you don't want to go through, well, not that you don't want to go through, but let's say that the alternative that I want to think about is given that the modern thing, is to use a deep network. How would I go about? How would I approach it? What would I need? What would I need to solve it as a using a deep network? First of all, you would need an architecture, right? That should maybe need not be something very fancy, but you want something like basic architecture. Will you go for an MLP or a CNN? A CNN because you have images. Therefore, that part is kind of decided. Would you need an RNN? Probably not, right? Because you just have one frame for which, right, you want the edge the pixels to be flat. So there's no reason to go for anything else. So it's clear that I need a CNN architecture, right? Then what else do you need? Right? You would need actually a data set, right? Which means, and what should that contain? That particular data set, what should it have? What should be the constitution of that data set? What should it have? It should have images, of course, and it should have a ground truth edge map, edge pixels. I mean, otherwise, how will you train it? Right? If you the simplest way to do training is to kind of think about some kind of a supervised approach. I'll come later. I'll ask you guys about more sort of a difficult question later. But let's just look at the simplest. The simplest is that I have an image, and for every image that I have, right, I need sort of an edge map. Now, who will actually give me the edge map? Can I use the canny edge detector? Huh. Exactly, right. So we're try to get something which is even probably superior to canny. If you give canny as a ground truth, then whatever you get can at best be canny. Right? It cannot beat the canny edge detector. So the issue is that you need a ground truth edge map which can come from a human. So that's where these human annotators are there. For example, in a lab it could be students, but then on a larger scale, right, it could be people to whom you pay to actually do this, and people are willing to do this. So what they will do is, as a human would sort of observe, right? If I gave you an image, so you as a human would sort of think that, right, these are all the edge pixels which I think are actually the most important and should be caught by an algorithm. So again, that's a little subjective. I mean, the same thing, give it to another person, that could be subjective variations, but it's okay. See, the whole thing about edges itself is that nothing is very concrete. Right? The very strong guys are very clear. The very weak guys are very clear. The in between guys are never clear. Right? And therefore, there's going to be some uncertainty across people. So if I gave her an image and asked her to draw an edge map, I don't think it'll be identical, right? I mean, if I asked right Anirudh to kind of do it, right? It may not be identical, but that is okay. But then right on in general, we feel that if you just give it enough number of people, those variations will get averaged out. And then the idea is now you need so you have sort of an input image, and then you show it an edge map, right? And then you say that this network should sort of do whatever it takes, learn the weights, have whatever, right, different layers, have these convolution operations, maybe do max pooling, whatever you want to do in between, and then eventually I should kind of say, right, spit out a result that should be very close to the edge map, right, which I have. Okay, this is how it should look. Now, one of the deep networks, right, that I thought I'll just briefly mention is what is called holistically nested edge detection. This came in 2015, and then an improved version of this came out in 2019. We'll take a brief look at both. So, for example, right, so if you kind of look at this, right, so here is I don't know, it looks like a leopard or whatever. So here, right, so here you have that. And if you really think about it, what are the most prominent edges in this image that you might want to catch? And if you actually give it to a human annotator, probably, right, he'll pick up something like that across people. Okay, something like that is what, because you will just want to look at what are all the major things that I want to catch in this image. Right. So the idea is that right now we are kind of going a little away now. Right. For example, we saw traditionally if you had to do it, right, then of course we would have had a certain way of doing it. But then now that right, humans are involved, so we can actually use the strength of humans, right, in terms of what they would interpret as edges and so on, and what could be important, edges and so on. So let's say, right, I mean, a human would probably annotate it, this way, and then you will have several such images for which you need the annotations, which is kind of a laborious, right? It's not an easy thing because somebody has to sit down and do all this. But once you do it, it's there, right? Anybody can actually use it. If it is publicly released, then anybody is free to use it. Then, if you kind of look at this, HED stands for this is a holistic edge detection. So this guy, right? So again, this architecture, is a little away from what we have seen in the sense that right, it also has some side outputs. I mean, in the sense that it has losses at every stage. Okay, again, right? That's what. So as I said earlier, also, right? Deciding an architecture, which architecture would work well for a problem. So people get those papers depending upon what they can show, right? I mean, if you can show that you have an architecture that solves a particular problem, and there is a reason to have that architecture the way it is, that is fine, right? So here these people argue that instead of just having one loss at the output, right? I mean, right, I mean, so what they're saying is instead of that, you could have actually multiple losses at every multiple losses in the sense that you keep showing the ground truth at every layer, and then you ask for the final output, and then eventually I think they take some sort of an say average, a weighted average of all the outputs that kind of say that emerge from each of the sides, like the side 3, side 4, whatever. Then there is a final. So the final output is like a weighted average of what actually comes out of that. Of course, there are some small things, right? Which if you read the paper, it will be clear. The idea is not to sort of explain the whole network and all that. The idea is to sort of say that there is a traditional way for right, doing edge detection, which we have seen, right, which we understand now. The question is, if I had to solve the same problem, given that it's a modern computer vision course, so if I had a deep network at my hands, and if I had the knowledge of training networks and all that, can I now, kind of recast this problem within the framework of actually, deep network and solve it? And that is the goal. And just a glimpse of what would happen. And right, holistic in the sense that it's kind of end to end. Okay, that's what this holistic, right? That's it's being used in that sense. And a nested because at every layer, right? I mean, right, you have an output, and it's inspired by fully convolutional. So all the way, okay, all the way till the end, right? It's actually fully this one convolutional for this one classification problem, and it takes images input, and the job is to directly produce the H map as output. So and then right, some other things, improved speed and all that. That's fine. And then the way this works is it's actually borrowed from VGGNet 16. So right, this is again one of the standard architectures that we already saw. So the architecture is the same. Okay, so they've taken the VGGNet and the VGGNet architecture, but what they've done is the last stage of VGGNet, which had the right FC layers and all, right? I mean, towards the end, I mean, how many? So you had something like four stages, right? And then after that, then you had a fifth stage, right? Which was the sixth stage maybe, right? I mean, you have like what 2 2 3 3 3, right? Something like 9 13 plus 316. Yeah. So I think what you had was 22333, right? That was the right? The VGGNet. And after that, you have the FC layers. So after the fifth pooling layer, so the one that comes after that, which are all the FC layers. So including the fifth pooling layer. So they say that they remove all of that and actually replace it, right? So kind of replace it with actually a convolutional layer. And that's why it's called fully convolutional. I mean, so nowhere are you having FC layers and all. So it's completely convolutional. And so what they are doing is after the last convolution, and then the side output layers are actually inserted after the last convolution layer in every stage. So for example, right, I mean, con one, which has actually two layer, I mean, right, two layers, right? So they're saying that after the second layer. Similarly, convol two after the second layer, then con three, because you have three layers, right? Therefore, after the third one, and similarly con four, con five, they all have three, right? Therefore, so what they're saying is after the kind of third feature map, right? So that is where they actually insert a side output layer, and they of course make sure that they say dimensions and all match. I mean, so for example, this dimension, because finally, right, if they want to take a weighted average, then you need similar dimensions, right? So that and all is taken care of. They'll have max pool and all, which then you will think that will not the kind of the dimension go down, but then there is something called a deconvol operation, which I didn't talk about, right? There's something called, just as you have a convol, right? there is also what is called a deconv operation. Actually, that's not strictly speaking, in actually traditional, signal processing. They say deconvolution, it actually means some kind of an inverse filtering. Okay, that's what deconvolution strictly means, but in deep network literature, it kind of abused. Okay, now this simply means that I mean, if you have reduced a dimension, right, then you want to kind of go back to the original dimension, but in a kind of a systematic way. Okay, so that right. I didn't talk about. You can actually read about it. It's nothing very fancy. It's straightforward to understand. So of course, you need that decon layer because you are kind of shrinking the dimension, but then you want to finally right do some kind of a weighted average, and therefore they all should match in terms of the size. So, but what they are showing is at the end of every stage, right? They're showing the output map, the output edge map that is needed, and there's a loss there. Again, at the next layer, show the output map. There's a loss there. I mean, these are all things that you can ask. I mean, why did they do it every layer? Could they not have done it in the third layer? But those are what are called ablation studies. So in that paper, they would have done all that. They would have shown that if you kind of do it otherwise, then basically it doesn't work that well. So all those are part of what is called, anytime you write a paper, there's something called an ablation that you have to do, which basically means that you have to prove, why you have these things, right, which you have there. You can't simply say, I like to have them, therefore they are there, right? Nobody accepts that. So you have to convince, right, the other, convince, whoever is reviewing, you have to convince them that all of this makes sense, which I'm sure, right, that's all there in the paper. So that's all the ablation studies. And then the final, right, HED output is a weighted average of all the M side outputs. And of course, there is also a final output of this, this one, a network. And they are computed only over the final output of this network, but on all the M side outputs, right, as I said. So now here is something, right, so that you can see. So what they mean to say is, right, so I think, okay, so what they mean is with deep supervision means that every layer, right, if you had this kind of a supervision, then right, I mean, according to them, what you actually end up in seeing, right, is actually much superior. They're not really having this kind of a deep supervision. Okay, so really without means that those side outputs, right, if you don't use that loss, then what happens versus using it. Okay, so again, right, these are all studies, okay, which they have which actually establish that. So in the first example, it's some kind of a bear, right? And you see that the I mean final output, right, looks actually good. And similarly, right, similarly here is actually a building example. And I think I have some more examples there. But then the point is, so the point is this, right? So you can actually solve the same problem. Of course, if you tried canny, right? So canny output is also given here, I think somewhere. Yeah. So for example, right, if you had tried canny, right, with let's say various sigma, so there is sigma equal to 2, there is sigma equal to 4, there is sigma equal to 8, you get something, right, like that. And of course, if you had a reduced sigma, then right, you will have of course more H pixels, and if you had even less, then of course you would have even more H pixels and so on. So if you try to compare this with this, right, probably this is not as great as what you have, for example, the output, right, that is emerging out of the network, and for obvious reasons, right, so because you are right, you are actually you are sort of giving the ground truth, you are showing what it should look like, and at the end of the day, right, that's where I think deep networks come up with this power that once you train them well, and once you train them with a rich kind of sort of a data set, then then when they kind of generalize outside in the sense of not too far away, but then as long as you don't have to show them the same examples, but they can still do a decent job, and it's very fast and all that, and therefore, right, these days, I mean, you have kind of deep networks that can actually do this edge detection job. But I think, the point is we should not forget the fact that we should also know where they come from, where these edges come from. See the problem with just doing a deep network is that if we had just learnt about how to do this, right, you won't even know what is an edge. Right, suppose I had skipped all of that, right, suppose right, we had not talked about edge orientation, edge magnitude, nothing we had talked about, and we said, okay, right, if you want an edge map, right, throw this ground truth, right, annotate and show, you will get an output, right, you will be able to maybe even arrive at a kind of network that does the job, but then your insights are rather weak because you don't even understand what is an edge pixel, right. That is the reason why we always straddle between both, right, a traditional thing where we actually where there is a firm grounding in terms of, because right, that is what was there all these years, and then using that knowledge, if you can do something, okay, right, in this case we are not really using any of that knowledge per se,
but if you can, right, that would be good. Okay, that's what I call like inspired. What do you call? What is that? What was in what inspired? What inspired? Physics inspired, right? Physics inspired deep learning. Right? That is like things that you have learned from a traditional approach, and then if possible use it. Let me ask you a question. Can this be done? I mean, if you ask me whether I have the answer, I don't have the answer either. Okay, but let me ask, right? Can this be done without a ground truth? What is called self-supervised learning, right? That's where the area is headed. How do you do an edge detection? How do I arrive at this output without me showing a ground truth? Can it self-learn to produce a depth map? Not depth map, edge map. Okay, then further improvement on this came in 2019, right, which they called richer convolutional features for edge detection. Actually, it turns out that I don't know whether it's the same bunch of authors, but roughly the network architecture, everything is the same in the sense that right, I mean you have a similar thing, but the only change that you see is that see, for example, so if you start from here, right, you're inputting the image from there, and then you have this is again a VGG net 16. So you have, right, two conv layers, then you have 3, 3, 3, 3, and then the final, of course, the final fully connected layer is all removed. But what you find is there, right, in the earlier one, I mean in the earlier one, right, so the feature loss was being calculated here, whereas here what is being done is both these channels are being used. Right. So you see that, right, so you see that this output is also being drawn from here, this output is also being drawn from here, then there is a 1 cross 1 convolution, okay, right, being applied on both, and those are actually summed up, and then again a 1 cross 1 convolution, and there is a loss here. Similarly, right, there is a loss, so that part is still the same, but then in between, right, they have shown that if you take information from every layer at that in every stage of the, let's say, VGG CNN blocks, then they say that, and then of course combine them in a suitable manner. So anyway, 1 cross 1 convolution and all we saw earlier, right? So it's a kind of very useful to be able to match this one dimensions and so on, and therefore okay, that they do, and then finally, right, what they do is they actually fuse. So the fusion is actually a concatenation here. So they simply concatenate there. It was a weighted average. Here they concatenate, and then follow it up with some 1 cross 1 convolution, and then of course then there is the final. Then there is also the output loss. And if you do it this way, it turns out that that actually, so the L-wise means, I think, right, element-wise layer. Okay, so if you don't wonder what that L-wise means. I think it's just element-wise. So here, for example, when you're summing up, right, it should be element-wise summation. Therefore, what they mean is, so right, you are able to do that, and then I think see this guy. That's that deconvolve block. Okay, that is the one that makes sure that your dimensions match up, so that you can concatenate and so on. And if you do this, then they show that, for example, the top line is the original images, from second to sixth line is the output of stage 1, 2, 3, 4 and 5 respectively. So you see that, right, so the scar has gone in, and then, right, this is what has emerged as the output. Okay, so right, this is the final output in a sense, and here, right, you have, so what you see is, there are finer edges in the initial layers, and they kind of probably combine, in a sense to evolve into more say meaningful edges, then they evolve into more and more meaningful edges, eventually leaving you with edges that kind of seem to be the most appropriate for the task. But this is all coming from a ground truth anyway, right? So you are showing a ground truth edge map, and they also show that show this kind of multi-scale algorithm. So by which what they actually mean is that that, for example, right, I mean, so if you actually gave this image, right, at the right, whatever, right, this one right, original size, and for which right, you have an output, then if you actually scale it down, just as I talked about the a Gaussian scale space, so you actually blur it, then you see scale it down, and then right, you try to find out the output, again pass it through the same network, then you get an output which is actually, right, reduced in size. But then the idea being that because of the blur, right, you would have probably masked out some of the unwanted edges and so on, and then if you again interpolate and bring it back to the original size of what you were getting from the actual size of the image, then you can go further down, do this, and then again you kind of bilinearly interpolate. Okay, so it's like a 4 neighborhood, right? That's what we mean by Just as in the other problem, we had linear interpolation, right, where we had only 2 pixels as neighbors, because when we were doing a gradient problem, here it's like it's like 4 neighbors you will have, and then you can do a bilinear interpolation and then bring it back, right. I mean, again, right, okay, depending upon the size by which you are going down, and then if you just combine them, right. So and then so this is what they call as a multi-scale thing. So it's the same network, right. They are not changing anything. One way is to simply use that network, push this image, and then this is what you get. Another way is you push the image, this is what you get. Then you kind of say push a down subsampled image, get this output, push another subsampled image, and then you show that the output of this, this is what you get. And then if you compare this with this, right, this is what you would have got with just one image. And then if you use a scale sort of a pyramid, then this is what you get. And their claim is this is slightly better. But again, I mean, you can argue. You may probably say that this is a little more sharper. Maybe right, you should actually accept that, but again, right, there is some paper that they have done and some analysis that they have done. If you take the weight, take simply the average, not weighted, I think just average them, then you get something like that, and they say that this is maybe the claim is that is actually better or whatever. Okay, so in all of this, so the key thing being that even right as as early, I mean as early as 2019, right, it's not like what by our standards it's not that far away. So you can still see that, right, even though you have deep networks and all, they still need a lot of supervision, right. So the real challenge is to sort of do it in a self-learning form, right. That is where the real challenge, and that's where I think your own input should come in, where you think in a certain way, where all your all that you learn, right, in a sort of a traditional sense, can that be brought to some kind of a bearing, right, into this problem, inject that into this, whatever, whichever way you want to do it.